Welcome to The Explainer. Today, we're taking a totally fascinating journey into the microscopic control rooms of the human eye. We're going to break down a brilliant clinical guide to the somatic and autonomic nervous systems, specifically zooming in on ocular pharmacotherapy. Now, right out of the gate, I want to give a massive shout out and explicit credit to the foundational lectures of Dr. Dirk J. Buissen. His phenomenal work forms the absolute backbone of what we're looking at today. So if you're the kind of person who loves knowing exactly how things work under the hood, well, you are definitely in the right place.
But first, I want you to think about a central mystery for a second. Have you ever put a single drop of medication into your eye and just wondered, how does it actually know what to do? I mean, it doesn't have a tiny little GPS system, right? It doesn't have a map. So how does one specific drop know to dilate your pupil, while a completely different drop knows to lower the pressure inside your eye? The answer is that your nervous system acts like this massive, incredibly complex control room. And those drugs, they're essentially molecular keys designed to fit perfectly into very specific biological locks.
All right, so here is our roadmap for the day. We're starting with a big picture macro view and systematically zooming all the way down into the eye cellular receptors. Our agenda is 1. The nervous system hierarchy. 2. Somatic versus autonomic control. 3. Fight, flight, and rest. 4. Ocular receptor mapping. And finally, 5. Targeting glaucoma with pharmacology. Let's get into it.
Okay, let's dive right into Section 1, the nervous system hierarchy. Taking a look at the absolute top of the structural tree, the human nervous system is basically split into two massive divisions. First up, you have the central nervous system, or CNS, which is your brain and your spinal cord. You can think of this as the main server or the central processing unit. Branching out from that, we've got the peripheral nervous system. These are the vast, sprawling communication lines connecting that central server to literally the rest of your body. You really can't grasp ocular pharmacotherapy without first understanding how a drug actually interacts with this peripheral network.
Now, it's absolutely crucial to understand that this peripheral system is a two-way street. Heading one way, we have afferent nerve fibers. These are your sensory fibers. They carry impulses from the receptors all over your body towards the central nervous system. Basically, they tell your brain what's going on. Heading the opposite way, we have efferent nerve fibers. These are the motor fibers, and they conduct impulses away from the brain out to the effectors, like muscles and glands. They're basically the brain's outbound commands, telling the body to take action.
And that naturally guides us down another level to Section 2, somatic versus autonomic control.
Now, what's really interesting here is how these efferent pathways, those outbound commands we just talked about, are beautifully isolated. They travel directly from the brain to target specific organs, like the eye. When the brain sends a signal down an efferent pathway to the eye, it uses a very specific structural channel. But here's the catch. These channels are divided based on whether you are actively thinking about doing the action or if your body's just running things behind the scenes.
And that division is exactly what we're defining here. The somatic nervous system handles all the voluntary control. Like when you consciously decide to move your arm or glance to the left, those somatic motor fibers are firing to your skeletal muscles. But then we have the autonomic nervous system. This is your body's autopilot. It involuntarily manages visceral organs, smooth muscles, and glands. You don't have to consciously remember to shrink your pupil when you walk outside into bright sunlight, right? Your autonomic system just handles it for you. And it's this exact autonomic autopilot that ophthalmic drugs manipulate so effectively.
Let's keep moving down the structural tree to Section 3, fight, flight, and rest.
This is such a brilliant illustration of the ultimate dichotomy within your body's autopilot. You see, the autonomic system is fundamentally split into two opposing forces. On one side, we have the sympathetic division. This is your classic fight or flight response. When you get scared or need to instantly spring into action, this system mobilizes you. It revs up your heart, constricts blood vessels in your skin, and dilates your pupils wide open to let in maximum light so you can spot a threat. On the flip side is the parasympathetic division. This is the rest and digest state. Its whole job is to conserve energy, promote digestion, and bring your body back down to a calm baseline, which includes constricting those pupils back down. They work completely opposite to each other to keep you perfectly balanced. All right, it's time to zoom into the micro level with Section 4, ocular receptor mapping. So here are the main classes of autonomic receptors that specifically relate to the eye: nicotinic, muscarinic, alpha-1, alpha-2, beta-1, and beta-2. The alpha and beta receptors are adrenergic, which means they belong to the sympathetic fight or flight team. The muscarinic receptors are primarily cholinergic. They're playing for the parasympathetic rest and digest team. You can basically picture these receptors as literal docking stations sitting right on the surface of your eye cells, just waiting for the perfect chemical messenger to activate them. And here is exactly how that activation mechanism works. An electrical impulse travels down a preganglionic neuron. Once it hits the end, it releases a transmitter, something like acetylcholine, across a tiny gap called a synapse. That transmitter binds to nicotinic receptors on the next neuron just to keep the signal moving along. Then finally, at the very end of the line, the nerve releases a transmitter directly onto the organ itself. If it's a sympathetic nerve, it drops noradrenaline, which binds to those alpha or beta receptors. If it's a parasympathetic nerve, it drops acetylcholine, which locks onto the muscarinic receptors. The physical shape of the transmitter fits flawlessly into the receptor, exactly like a key into a lock, instantly triggering the eye to react. Now, this matrix right here, this is the absolute core of ocular pharmacology. It perfectly maps out cause and effect. Take the iris dilator muscle. It's packed with alpha-1 receptors. When the sympathetic fight-or-flight system dumps noradrenaline onto those alpha-1 receptors, the muscle contracts, causing pupillary dilation. More light enters, so you can see danger. Conversely, look at the iris sphincter. That one's loaded with muscarinic M3 receptors. When the parasympathetic system activates them, the sphincter contracts, causing pupillary constriction and returning the eye to a rested state. So, if you're a doctor and you need to forcefully dilate a patient's eye for an exam, you just use a drug that artificially mimics that sympathetic alpha-1 activation. You are literally hacking the system. So, the crucial point is, how do doctors use this incredible map to actually treat diseases? Let's bring it all together in our final section, Section 5, Targeting Glaucoma with Pharmacology. Glaucoma is very often managed by controlling the intraocular pressure in the eye. And the sequence to do that is incredibly precise. Let's trace a topical anti-glaucoma drug, specifically a beta blocker. Step 1. The patient administers the topical drug. Step 2. The drug bypasses everything else and specifically hunts down beta-2 receptors located in the epithelium of the ciliary processes. Why? Because naturally, when the sympathetic system stimulates those beta-2 receptors, they crank up the production of aqueous fluid in the eye. Step 3. The beta blocker physically binds to these receptors, completely antagonizing or blocking the body's natural transmitters from attaching. It basically puts a piece of tape over the keyhole. And finally, Step 4, because those receptors are blocked, the stimulation stops and there is a significant drop in aqueous fluid production, safely lowering that dangerous pressure inside the eye. It's just targeted structural brilliance. Which leaves us with this final, really thought-provoking question. We know that some current drugs, like non-selective beta blockers, can sometimes cause systemic side effects because they accidentally block beta receptors in the heart or lungs too. But as we map these autonomic pathways with even greater precision, could we soon design ocular drugs that perfectly target just a single, highly specific receptor subtype in the eye, effectively curing conditions like glaucoma with absolutely zero side effects? The control room is already mapped out. Now it's just a matter of designing the absolute perfect key. Thanks so much for joining me on this explainer, and keep questioning how the incredible machinery of your body actually works.